All right, I think everybody is connected, and let's get started. So, so today we're going to continue talk about transmission. That will be chapter 25. We will finish chapter 25, and next week will be our last week, and we will talk about the last mile of electrical delivery. That will be the medium and low voltage. So that's what our plan is. So today we'll keep talk about the high voltage. So the high voltage delivery is very well studied, obviously, because billions of dollars are at stake.
Anytime you can make this system even 0.1% more efficient, you will save thousands, if not millions of dollars per day. So huge impact of because the larger the scale is huge. So everything is very well studied for this system. And this system is so complicated, obviously, there's no way we can analyze this if we think about all those complicated details. So what we did is we simplify. So the number 5 is the simplified version of our power delivery system, number 5. So number 1, it's first, the power delivery system is mostly inductive. So if you think about a power line, power grid, long distance power line, the obstacles is overcome the inductance. Also resistance, but resistance is to a lesser degree compared with inductance. So resistance and inductance, they are both limiting factors, but the most obvious one, the more important one is inductance. So we want to build a transmission line with the least amount of inductance. Least amount of inductance. That way we can transmit more energy through the current transmission lines. So that's the first thing we want to talk about. Second thing is for the inductive transmission line, the power it can deliver will be, for example, 50K. We can double that. So we can double the amount of power can be delivered from the same transmission line if we compensate on the other side with a capacitor. So this is why we have a capacitor over here to compensate the inductance. So this variable capacitor will, if we perfectly match the variable capacitor, in theory, we can double the amount of power we can deliver to the customer. Yeah, that's great. So we can basically double the amount of energy we can potentially deliver. So that is the second thing I want to talk about. First is inductive. Second, you need a capacitor to double that capacity on the customer side or on both sides. Third, the customer is always changing. The customer, unlike anything else, the utility power grid, the customer is changing every second. So your customer is change all the time. What happens when your customer changes all the time? The demand for power changes every second. And that will create a potential problem for this system. So in order to make the whole system safe, this matching capacitor need to be variable. So this capacitor need to be varied in real time to match the load. So when your load increase, you increase the capacitor. When the load decrease, you decrease the capacitor. When the load decrease to a certain level, you completely cut off the capacitor. There's no need for capacitor. And then if load continue to decrease, you actually need to add an inductor. Well, that's amazing. You have to need an inductor. So that means on the customer side, when the power arrived at, for example, a city, you need a variable capacitor or inductor. So this is the variable inductor. So you need a inductor or capacitor. Ideally, you have both to make a compensation. So figure 37 is a inductor. That means if your customer is a underload, so your customer is not using a lot of power, you need inductors to make compensation so the voltage delivered will be safe. Otherwise, the voltage can go, the also did example, voltage can go almost 50% higher than the source, 50% higher than the source. So you need an inductor, you need a capacitor. It's all depend on the customer. So it's not easy. You have to keep monitor in real time and make the right decision to attach a reactive device in the customer side. So the power delivery will be safe and potentially you can have maximum amount of power delivered. That means in this particular example, that means 100K. But if you take care, if you consider the 2 ohm resistance we have over here, that means about 20% probably will be lost on the, we call it copper loss, lost on the resistance. So the maximum power will be delivered in this scenario will be 80% of the theoretical maximum power will be delivered. So that's the whole theory. And under this theory, this is what happens in the real world. We put the big inductors and the big inductor slash capacitors to make that compensation. So the whole power grid will behave normal, behave safe, and behave economically, provide the maximum amount of power potentially to our customer. So that is the summary for the theory, simplified theory. I think I'm pretty sure in the real world it is much more complicated than this simplified mathematical theory we covered here. So this is just simplified. But the theory is basically a guidance for the field. So the practice in the field have a theoretical basis. So we do something not because uh, the only reason we do something is because we want it. There's a theory behind it, and it, more importantly, it works in the field. So that is what we covered last time. Today we have one more topic. The last topic is this one, this guy right in the middle here. So last time we covered scenario 1, 2, 3, 5. 1, 2, 3, 5, right? 1, 2, 3, 5. Number 5 is the most accurate model. Number 5. How about number 4? Any questions before we move on to our number 4 new topic for today? So if we don't have questions, comments, we will move on to our next topic. Today's topic will be number 4. Number 4, we dealt with interconnections. This can be St. Louis. This can be Kansas City. So on one side, we have Kansas City. On the other side, we have St. Louis. So there's 2 power grid, 2 different companies. And they can operate as an island. They can do it, operate as an island if they want it. But it make more sense. They don't. They interconnect. It makes economic sense. It makes everything more reliable. It has a lot of advantages to interconnect. How do you interconnect? You just have a jumper, right? Connect both. That will be like a 300-mile or 200-mile cable. And again, it's inductive. For example, it's 10 ohm inductance. So let's study what will happen if we interconnect 2 islands into one bigger island, right? We can interconnect 2 islands into one bigger island. Actually, I was reading this on some latest news. There are there are proposals even for all the power lines around the world will be interconnected. Right now, the power, for example, America, Canada, Mexico, and then you have Europe, you have Asia, right? They are not connected. Well, they actually have a talk of united nation of power, united power. The whole world power grid will be all interconnected. It sounds like a dream. There's a lot of advantages, but it's another way. Now we have internet, right? When you 30 years ago, if you talk about the whole world is connected by one computer network, you were thinking about they are dreaming, right? Now we were talking about the whole world power grid interconnected. Anyway, so what happens if you wire them together, connect them together? That's the study we're going to do today. That is the power exchange. So you have region A, Kansas City. You have region B, St. Louis. And then you have a wire, extra wire. So those wires are between two islands. You have one island, you have another island. The two islands is interconnected together. What happens is the power potentially can exchange. You can exchange power from A to B or from B to A, or nothing, or nothing. So what determines the power exchange? It turned out one simple equation determines the power exchange. That's the equation. Voltage square divided by X, X is the inductance, multiply cosine delta. What is delta? Delta is the phase angle between the two regions. The two regions are all 60 Hertz. So St. Louis, Kansas City, all 60 Hertz. But the phase angle might be different. So it's all depends on the phase angles. If Kansas City phase angle is 11 degrees ahead of St. Louis, then Kansas City will pump 95.5 megawatts of power to St. Louis. So it's all about the delta. So if the delta is 11 degree, if Kansas City is 11 degree ahead of St. Louis, Kansas City will provide 95.5 megawatts of power. Otherwise, if St. Louis is 11 degree ahead of Kansas City, St. Louis will deliver 95.5. What about the, you add 20 degree. If it's a 20 degree, let me do the math. 20 degree, it will be more power. 20 degree. Multiply. So if it's 20 degree, it will be 170 megawatts. So it's all about the phase angle. The more differences, the more power it will exchange. So the amount of power exchange is depend on the delta, the phase angles. What if the delta is 0 degree? If it's 0 degree, it will be 0. There's no power exchange, 0. No power exchange. Here comes with the question, how do you control that delta? So obviously, when you interconnect two islands, you want to control the amount of power flow in between the two islands. How do you control that? That is controlled by a phase shift transformer. So there is a transformer. The only function of the transformer is change phase angles. That's a special transformer we covered when we talk about transformers. So a phase shift transformer is a transformer in between the interconnections. So by altering the phase shift transformer, by control that, we control the phase angles. By control the phase angles, we control the power exchange between the two islands. So, and today, those auto transformers is controlled, again, obviously by networked computers. So a networked computer will send out commands, and based on the agreement, based on the purchasing agreement, because every time you exchange power involve exchange of money. So based on the season, based on the demand, and they exchange power. And this power exchange is pre-programmed to the computer. So the computer will send out the commands to the phase shift transformers. And phase shift transformers will control the flow of energy, either left to right or right to left. So that's the fourth scenario. What is the maximum amount of energy can be exchanged theoretically? In this scenario, the maximum amount of energy can be exchanged between the two islands is 100K. Again, it's the same transmission theory. You are transmitting power through an inductive line. And the maximum amount of power potentially can be transmitted depend on the inductive line. So there are a lot of factors determine the maximum amount of power. So the maximum power can be transmitted is limited, but how much power is transmitted also determined by the delta. So if you can do zero, if the both island is okay, they don't want power, they don't want to buy power from each other, and we just set the delta to zero, and there is no power flow between the two islands. All right, that's the theory. Also followed up by an example. The example is New York and Connecticut. So that is a Long Island. That is ocean, I think, water. So you need to. One side is New York, one side is Connecticut. So two island. So that's the power grid of Connecticut. That's the power grid for New York. And it was decided to install a phase shift auto transformer at Northport, right here, Northport, right here. So there is a phase shift transformer right there. By control the phase angles, the transmission line between the Norwalk and the Northport. So there is a transmission line, 6 cables underwater. That's the cable. So the conductor is right in the middle. No, conductor is not in the middle. The conductor is, where's the conductor? Copper, that's right there. So these are the conductors, copper conductors. Notice the copper conductor is hollow, filled with oil. Outside the copper conductor, there is a paper. Outside the paper, you have lead jacket, lead. Outside the lead, you have a polyethylene.
Polyethylene.
Polyethylene, yeah, there's a E, polyethylene, thank you. What's that?
What's what?
What's polyethylene?
Oh, it's a pretty common plastic that's petroleum based.
All right, we have an expert on that from Shenzhou Plastic. All right, common plastic, okay, thank you. Outside that is a steel jacket armoring. So they have to have steel armoring because this is a steel armoring. Because it's underwater, they might have sharks, right? And they might bite on that. So protection jackets, steel protection. So they have 6 of those cables, start from here and on the other side. And they have a phase transformer at here to control the flow of energy up to 300 million watts. The phase shift is a positive and negative 25 degree. Yeah, it's both positive and negative. So you can shift that phase angle, positive, negative, that will control the energy flow. So if New York need more energy or Connecticut needs some help, we can control that. And up to 300 megawatts. The length of that line is 19 kilometers. 19 kilometers. That is why for long distance, we must have aerial. This is only for short distance. Why? Because of this. Yes, notice the capacitor is only 700 ohm. That is very low resistance, very low impedance. So potentially a lot of power can drain through those 2 capacitors. So underground cable or underwater cable can only be used for a few miles. Anything longer than a few miles, in this case, is about 10 mile. So less than 10 mile or about 10 mile. The longer, the more loss. That's the maximum distance it can deliver for underground. My neighborhood, the power came from underground cable. It just so happens because there is a substation about a mile or even less than a mile, walking distance. I literally can walk through my neighbor and reach that substation. So that's why it's very close, 10 mile. Anything longer than that, you need an aerial because this can be too much. By too much, I mean too little. The number became smaller and smaller, and there's no power can be delivered when those numbers are too small. The power all goes to the ground. So your customer get nothing. So that is why for local power delivery, there's a new technology called the DC power line. So instead of AC deliver power, you deliver power using, instead of AC, you deliver power using DC. For DC, those capacitors, we don't care. We don't care about that capacitor. As long as we have good insulations. Yeah, all you need is good insulation. We have very good insulation. We have paper, we have lead. I think the lead is for moisture. So, and then we have plastic. We will insulate and moisture. Anyway, so for DC power delivery, it's more feasible. Another reason for DC power delivery is underground. So if you want to deliver any power underground or underwater, the only feasible way, or the feasible way to do it is DC. So let's continue read a little bit about this power cable. It's a 10 mile long, what is the resistance? 1.3 ohm, 1.3 ohm, and the inductance of 1.1 ohm. So of those 10 mile, you have the inductance, you have the resistance, and you have capacitance, which is 700 ohm on both sides. So I haven't studied this. So obviously it will be ideal if you have an inductance to compensate those capacitance to make it handle more power. So the table here give a submarine cable. This is also works for the underground cable. So for the total power, for the reactive power and delivered power, the total power loss, so very small because the short distance, 3 megawatts of copper loss. You may think it's a lot of energy wasted, 3 million watts, but compared with the power delivered, 300 million watts, it's just 1%. So it's 3 million, you think it's a lot of power, but consider 300 million delivered. So it's okay. The inductive is 2 million, it's nothing. Most important is the capacitance. The capacitance became a huge factor. That is why they only can do short distance, because as the distance get longer, this became out of control, reducing this to a tiny number. So when that increase, this will drop. So it makes no economic sense because all the power goes to here, no power to the customer. So that is what we want to cover for today. We ended chapter 25. There's one more chapter left, distribution. Last mile, or last 10 mile. Yeah, should say last 10 mile, or last 20 mile. So there's a lot of topic in chapter 26. So because we have about 10 minutes, I will just get started. So any questions for chapter 25 before we move on to 26? So chapter 26, we talk about the last 10 miles. The last 10 miles start with something like this. So this is a very good picture, figure 24. Figure 24 shows an aerial view. So the aerial view of a substation. So that is your high voltage power line. On the very right, we have hundreds of thousands of high voltage arrive from the right, And what is on the left? Number 8, those are the medium voltage goes to every neighborhood inside that city. So if this is Shenzhou, for example, that will be the high voltage power arrive at Shenzhou. And on the other side will be the medium power goes to a different neighborhood, like north, south, Missouri Western, all different customers. In this particular example, they have 36. Out of 36, 30 are used, 6 as a backup. So there's 6 medium voltage outlet as backup. So goes from right to left. What is number 2? Number 2 is the circuit breakers, just like in your house. If you go to your basement, what is the first thing you see after the power arrives your house? You have a circuit breaker. Same thing. You have a circuit breaker. And what is after? After the circuit breakers are the switches and the circuit breakers. So number 2 are switches, actually not circuit breaker. Number 2 are switches. So you have switches before, switches after. So you have 2 switches. Those switches are motorized. They look the same as any switch, it's just big. How big? I'll show you a picture of those switches. That's big. Figure 10 is a switch. Did you see that switch? That's a big switch. This is motorized, go up and down, open and close. They designed it as a big visual, so the technicians can instantly see if switch is open or closed. So they are designed to be very, oh yeah, that's a switch. Close and open, close and open. That's a switch. So on the substation, you have switches. Right in between the switches, you have circuit breakers. After the switches and circuit breakers, number 4 is transformers. 1, 2, 3. You have number 4 as backup. So generally, only 3 are needed for 3-phase. But they put an extra one just in case one of them, blow up, and you can quickly rewire to the backup transformer. And after the transformer, number 5, what is number 5? Number 5 is a medium voltage bus. So the medium voltage bus is number 5. And number 6 is grounding transformers and the circuit breakers. So you also have circuit breakers. You also have grounding transformers. That is provide ground, create a ground. What is the ground requirement? Did you see that? 0.1 ohm grounding resistance. Previously, when I talked about high voltage transmission line, we say 10 ohm grounding resistance is acceptable on those big towers. Well, in a substation, the grounding resistance typical 0.1 ohm, 0.1 ohm. So this ground is probably they drill very deep and attach the ground that way. So that's how they get that 0.1 ohm. 6 and 7, number 8 will be the 36. Some of them are aerial, some of them are underground. So for example, in Shenzhou, we still have a lot of aerial medium voltage power lines. In the old neighborhood, old part of Shenzhou, the newer development mostly has underground because it's much safer and reliable underground. And of course, the last component will be the customers. So those are the customers, number 9. So that gives you a big overview of substation, what need to be taken care of. This is a big substation. It's a lot like the substation near my house. There are smaller ones around Shenzhou. I'm not sure how many substations Shenzhou has, but I actually follow the transmission lines on Google Map. I follow the transmission line about 10-20 miles. I followed them. It reaches another substation. So that's what the results. I didn't follow after that because it's kind of difficult. You can do it on Google Earth, right? Google Earth or Google Map, satellite view. So the satellite view is good enough to follow those high voltage power lines. It just goes through all the farms, a lot of farm. In between, I noticed in between the two substations, there are some wind turbines in the farm. So there are a lot of wind turbine in between. So that is a substation. Now the first component we want to cover for the substation are the circuit breakers. Circuit breakers. Basically, is the exact same circuit breaker you have in your basement. So in your basement, your circuit breaker, only bigger. So the circuit breaker in your basement is like this size, right? Like a remote control size, or cell phone, the size of your cell phone. How about this? It's the same principle. It's only bigger. How big? This is one example of a circuit breaker. It will cut off the power in 3 cycles. So it is not cut off instantly. It cut off in 3 cycles. It is 10 feet tall and 10 feet in diameter. So it's a big 10 by 10, 10 feet by 10 feet. $21 tons. So that's one example of circuit breaker. There's another circuit breaker example. This one is even bigger, 15 feet. So this one is even bigger. This one is look like a tank. So it's an oil circuit breaker. Why oil? You might think oil is dangerous, right? The circuit breaker has a lot of sparks and spark and oil. Yes, actually they generate sparks. They burn, they create sparks. Well, it's pretty safe because there's no oxygen, I would think, because the oil, you have to mix them with oxygen. If there's no oxygen, it's just a little spark. The circuit breaker can also be air circuit breakers. Looks like figure 4 is an air type circuit breaker. Air type. The circuit breaker can also be a special, not oil, not air. It's a fluorescent What is that? I don't know that. That's a chemical gas. So this is a special type of gas. There's a picture, figure 7, this type of circuit breaker. Why this circuit breaker? Because it's a low noise. So this type of circuit breaker is used in the metropolitan area where there's a lot of noise and other regulations. So that's a special type, Far less noisy. I'm not sure about how noisy the air one is. Let's do a YouTube video. The last one will be vacuum circuit breaker. Vacuum circuit breaker. So this is a vacuum circuit breaker. So there's a 4 different type of circuit breaker depend on the applications. Some use a vacuum circuit breaker because in vacuum you will not have a spark. In theory, you cannot generate spark if it's vacuum. This third type is less noisy. And then you have air and oil types. Figure 5 is the air type. Figure 6 is also air type. So circuit breakers. So that's the number 1 component, circuit breaker. Any questions?
So,
Circuit
I guess do they all look generally like that, or is there just a whole different, variety of housings and stuff for mechanisms like that?
I think besides the air type, the oil type look like a big oil tanker, right? A big oil tank.
Oh, that's it. Okay.
Yeah, the others just look different. Yeah.
Mm.
Yeah, they look different. Let me watch. There's a lot of YouTube videos about the circuit breaker, about the
That was cool.
400K voltage. This is not a circuit breaker. This is not actually open switch. So motorized switch.
Wait, so that's just the switch turning off.
Yes,
and that's it turning on.
Yes. Yeah. That's turning on. That's turning off. So that's it. That's that's the cutting off the power. That is a switch. Exact same thing will happen inside the circuit breaker. It's the same thing. Circuit breaker just open it for protection.
In your home.
Yes. So it's quite dangerous when you're talking about 100,000 voltage and thousands of amp of current, and extreme dangerous. Any other comments about that? I uploaded the exit exam, so do it. So I think Craig, who else? Vince, Lauren, Ian, and Blake. 5 of you. Just go to 422. I prepared a special quiz for 5 of you, and those will be your exit exam. All right. If we don't have anything, I will see you guys next Monday. And have a good.
Well, all right.
Yeah.
Well, thank you.
Yeah. Have a good weekend.